Assalamu alaikum. Welcome to the next class. Today we'll be doing the phasor relationships for circuit elements. So we know that we have three types of circuit elements. They are resistance, inductance, and capacitance. So in time domain representation, we know how they can be represented, but now we need to find out their relationship in phasor form so that we can solve the circuit in frequency domain. So we know that how to represent the voltage and current in the phasor or frequency domain that already have been discussed in the previous class. So we have to apply the same thing to the passive elements like R, L and C. So what we need to do is to transform the voltage current relationship from the time domain to frequency domain for each element as we have done for the voltage or current. Again, we'll be using the same passive sign convention. They are very important, and I have already discussed what are the different passive sign conventions. Now let us start with the resistance. We begin with the resistance. If the current through a resistance is Im cos of omega t plus phi, so we have started from the current itself. The voltage across it is given by the Ohm's law. That is equal to V, that's the instantaneous voltage, will be equal to instantaneous current multiplied by the resistance. So it is equal to R as it is, and the time varying current I, that is Im cos of omega t plus phi. This is the time domain representation. This is the phasor representation which is used in the bold form. The phasor form will be that V is equal to R into Im angle of phi. Because we have converted this to phasor form, we are only retaining the maximum value and the angle, and we are dropping this cos in omega t. So it comes out to be V is equal to R into M at an angle of phi. But for the phasor representation of I, that is current, it is equal to Im angle of phi. Because when this is represented in terms of phasors, this I, that's capital I, will be equal to Im angle of phi. So that means this will be converted to a capital I, that is this V is equal to IR. This means that this voltage current relationship for resistance in time domain is V is equal to IR. This also holds good in phasor form or frequency domain relation. It remains same as that is called as it is as V is equal to IR. So this is illustrated over here, and this is also illustrated in terms of the phasor form. Let us say this is I, which is equal to I at an angle of phi. That is this I is equal to Im at an angle of phi. That is this phasor. It has some angle phi with respect to some reference, that is real axis. So what is V? V is also having some other magnitude which is equal to R multiplied by M. Assuming that R is greater than 1, this V will be greater than this I. So this will also have the same phase angle. That means we can see it from here that this voltage and current will be in phase in case of a resistance. So this is very important. So to do the same analysis for an inductor, let us assume again the same current I is equal to Im cos of omega t plus phi. The voltage across the inductor, as we know, is equal to L di by dt. So we have to multiply this. We have to first differentiate this term I with respect to t and multiply it by L. When we differentiate this with respect to t, it will be equal to minus Im omega sine of omega t plus phi, that is this minus omega Im sine of omega t, and multiplied with this L, it comes out to be this term. So converting this to again a cos, we know that cos of theta or a plus 90 will be equal to minus cos of a. We have actually we have to change the sign to cos, and we have to consume this minus inside this. So we use this formula to do the same. So we'll change this cos, this sign will change to cos, omega t plus phi will remain as it is. The only thing is that we have to add plus 90 degree over here. It comes out to be like this. So which is the transform of the phasor. Sorry, which is the time domain representation of the voltage across inductor like this. So in the phasor form, this V L I M, this cos omega t plus phi plus 90 can be converted to like this, because we have to retain only this term cos and omega t have to be cancelled out. It comes out to be, I can recall it like this, omega L Im e raised power g5, that is this, and e raised power j90, that is this. While e raised power j90, as you know, it is actually equal to be equal to j, because this term will be equal to cos of 90 plus j sine of 90. Cos of 90 will be 0 plus j sine of 90 will be equal to j into 1, that will be j. So this term will be equal to j omega, this will be j, sorry, this will be j omega L, and this Im e raised power phi, that is equal to Im angle of phi. It is actually the phasor I. So V, that is the voltage across inductor, will be equal to this j omega L into the phasor I, showing that the voltage is the magnitude of omega L into Im. It is the voltage magnitude, and the phase angle is phi plus 90 degree. That means when we use in terms of the phasor form, this is I at an angle of phi with respect to this real axis, but this voltage, you can see it is at an angle plus 90 degree with respect to this current. That means this voltage in case of an inductor leads to this current by 90 degree, but you need to be very careful here. This voltage and current are the voltage and current of the inductor itself, that is voltage that is appearing across the inductor and the current that is flowing through the inductor. That is what is which relation we are talking about. That means the voltage across inductor leads to the current flowing through the inductor by 90 degree, or conversely we can say that the current that flows through the inductor lags to its voltage which appears across this by 90 degree. This is also very important. So coming to the capacitor, let us now assume a voltage V, Vm cos of omega t plus phi, as the voltage that is appearing across the capacitor. I have here assumed voltage. In previous cases I assumed current. It is just for the convenience, because just if I have assumed here I, then I have to integrate it, but to differentiate it, and then I have to calculate some constant of integration as well. So to avoid that, I just use the voltage itself and calculate the current. The current that is flowing through the capacitor is given by this relation, I is equal to C dV by dt. So this also we have derived earlier. So the differentiation of this voltage will be equal to minus Vm sine omega t plus phi into omega multiplied by this C. So it comes out to be, when going to the same steps, converting cos sine into cos, consuming the minus, it comes out to be this I will be equal to j omega c into V, or V is equal to I divided by j omega c. So you can see it from here. When we are using the phasor diagram, we have assumed voltage to be at an angle of theta with respect to this real axis, and the current comes out to be 90 degree. You can see this J means a 90 degree shift, positive shift from this voltage. Same was the case in case of inductor, because we have assumed this 90 as J, and J means that this voltage is ahead to this current by this angle J. Same is the case over here. Here we have current that is leading to this voltage by 90 degrees, that is shown by this phasor diagram. So I repeat this sentence. That means when a voltage V is appearing across this capacitor and the current flows through this capacitor, their phasor relationship is such that this current leads to this voltage. This current leads to this voltage by 90 degrees. Or conversely, in case of a capacitor, the voltage lags to the current by 90 degrees. But usually we always talk about current with respect to voltage. So in general, in case of a resistance, let us try to have a tabular form. In case of a resistance, you will see that voltage and current are in phase. In case of an inductance, you will see that this voltage leads to the current by 90 degree, or in general, when we are, as I have told you, that we are always talking about current with respect to voltage, the current lags to this voltage by 90 degree. In case of capacitance, the current leads to this voltage by 90 degree, or voltage lags to this current by 90 degrees. Let us try and to do one numerical to have some basic concepts regarding the same. So Let us say the voltage V is equal to 12 cos 60t plus 45 degrees is applied to an inductor whose value is 0.1 Henry. Find the steady state current through the inductor. So first we need to find out the steady state current. So what is the value of L is equal to this? V is given to be, we'll first convert this V into phasor form. V is equal to j omega L into I, where omega is equal to 60 degree, that is this omega. And when we convert this V into the phasor form, this comes out to be 12 at an angle of 45 degrees. So V is given. Omega is also given, L is also given, so we need to find out this I. So we just divide this voltage by this j omega L. I will get value of I. So I is equal to V divided by j omega L. This is 12 at an angle of 45 divided by j into 60 into 0.1. It comes out to be 60 at an angle of 90 degree. It comes out 2 at an angle of 45 degree. Again, converting this to time domain, I will get IT is equal to 2 cos of 60t, because this remains as it is, minus 45 degree. Here also you can see that this current lags to this voltage by 90 degrees. They have voltage relationship because this is having a plus 45 degree with respect to some reference. This is having a minus 45 degree with respect to the same reference. So the net angle difference between the voltage and current will be 90 degrees. So now coming to impedance and admittance. In the preceding section, that is, we just have calculated V is equal to R into I in case of resistance, V is equal to j omega L into I in case of inductance, and V is equal to 1 divided by I divided by j omega C in case of capacitance. So in general, we know that the impedance or we can write them in terms of V divided by I. So V divided by I for this is equal to R, V divided by I is equal to j omega L, and V divided by I for this is equal to j omega C. And for these expressions, we can see in general, these terms are nothing but the impedances. You can see V by I in general are the impedances. So this Z is equal to V by I, or V is equal to Z into I. By comparing these two equations, you can see the impedance of the resistance is equal to R, impedance of the inductance is equal to j omega L, and impedance of the capacitance is equal to j omega C. And this impedance Z is the frequency dependent quantity known as impedance measured in ohms. Have to be very careful about these things. And the impedance Z is the ratio of the phasor voltage V to the phasor current I. It is measured in ohms. The impedance, like the resistance, we have already known what resistance does. It actually opposes the flow of current. The impedance does the same thing. The impedance represents the opposition to the circuit, exhibits to the flow of sinusoidal current. Although the impedance is a ratio of two phasors, but it is not a phasor because it does not correspond to a sinusoidally varying quantity. It is a constant quantity. So you need to be very careful about this. There are two things which we have just discussed, that the impedance exhibits the opposition to the flow of sinusoidal current. Since it's the ratio of the time varying quantities, that is voltage and current, it itself is not a sinusoidally varying quantity. It's a constant quantity only depending upon the frequency, so that we can see that it is not a phasor. The impedance of resistors, inductance, capacitance can be readily obtained from equation this, which are summarized in terms of this table. That is, R is the element resistance whose impedance is R, and admittance is given as 1 by R. For L, impedance is j omega L and admittance is 1 by j omega L. Admittance is nothing but the inverse of this Z. For C, Z is equal to 1 by j omega C. Sometimes it may be written as minus j by omega C, because 1 by j is equal to minus j. So Y is equal to j omega C. One more thing we have perhaps discussed earlier, but only the DC case. When for a DC, this omega is equal to 0, that means Z is equal to 0 for an inductance. That 0 means it's a short circuit. So inductor acts as a short circuit for DC. And for higher frequency, you can see higher frequency, very high frequency, this Z may tend to infinity. And infinity in case of electrical network means, and Z is equal to infinity, is an open circuit, because open circuit there will be no flow of current, and V by Z, V is having some finite value, Z has an infinite value, so some finite or infinite will be 0, that means an open circuit, there will be no current. Similarly, for a capacitor, it appears to be as an open circuit for a DC because omega is 0, impedance will be infinite, there will be no current, it will be an open circuit. And for high frequencies, you will see that this comes out to be equal to 0, it will be a short circuit. So in general, inductance will appear as a short circuit for a DC, whereas capacitor will act as an open circuit for a DC. Now, this is very important, and from here you should be very cautious about the impedance. Now, as a complex quantity, impedance may be expressed in a rectangular form because sometimes you may have a combination of impedances. Let us say we have R and we have this L, and their impedance will be R plus j omega L. So in general, we actually express the reactance of the inductance as XL, or an this reactance of the capacitor XC. But in general, to combine them, we drop the subscript XL, and XC we generally call the reactance as X. So depending upon that value, that's why I kept it as G of X. If it is inductance, that means this X is equal to omega L. If it is capacitance, that means this X will be equal to omega. This X will be equal to minus omega C. So where R is the real part of Z, you can see this R is the real part, and X, that is the resistance, and X is the imaginary part of Z, that is the reactance. This reactance may be positive or negative. It depends upon the value of this XC and XL, because this is in general R is this R plus JX. You can see from this diagram, this is R, it will always lie in the real axis, and in imaginary axis J omega L will lie, that is ZL will lie on the positive J omega axis, and this ZC, since it is called minus J omega C, it lies on this minus J omega axis. So what I mean to say is that this X is actually the summation of these two, summation. So if the ZL is more as compared to this X will be positive, the total circuit will be inductive in nature. If this XC or ZC is greater than this, that's magnitude is greater than this, the total, this will be negative, that means this part will be negative. In that case, the circuit will be capacitive in nature. So when this happens, the reactance X may be positive or negative. It will be positive when ZL will be greater than ZC, and it will be negative. This X will be negative when ZC will be greater than this Z, and it will be 0 when they are equal. So when this is inductive in nature, you can say the current will lag to the voltage by some angle, depending upon this angle, whatever the angle between these two are. And if the ZC is greater than this, the circuit will be capacitive. In that case, the current will lag to this voltage by some angle, because earlier I told you that in case of inductance, current will lag to the voltage by 90 degree, but here, since the presence of R, the angle which was earlier to be equal to 90 degree, it will be slightly less because of this R. So same is the case over here. In the pure capacitance case, the current reduces the voltage by 90 degree, but because of the presence of R, the angle will be slightly less as compared to 90 degrees. So leading because of the impedance, resistance, and reactance are measured in room. The impedance may also be expressed in the polar form. This is a polar form, but it is not a phasor form. As I have told you that this impedance is a complex quantity, it is not a phasor form. So its rectangular form is this, and its phasor form is this, where Z is equal to square root of R square plus X square, and theta is equal to tan inverse of X divided by R. So you can, that is given over here, is Z is equal to R plus JX, which is equal to Z. This magnitude of Z at an angle of theta, where the magnitude of Z is equal to square root of R square plus X square, and theta is equal to tan inverse of X by R. So here R is equal to, this R is equal to Z cos of theta, and X is equal to Z sine of theta. This can be represented in terms of an impedance triangle. This is known as impedance triangle, while this hypotenuse denotes the Z, that is this Z. I have denoted here over here as Zm, but it is this Z. So here it is denoted phi, that is the angle of this Zm with respect to real axis. This is the angle theta over here. So this component, which is the sine component, it will be x. You can see x is equal to z sine theta. This x will be equal to z sine theta, that is over here. So this cos component will be the r will be equal to z cos theta. So from here you can use this impedance triangle to find out the real part and the reactive part, or in general you can find out the value of this resistance and reactance from this impedance triangle. You can also note that when this r is equal to 0, which is the case which we have already discussed, this tan inverse of x by 0 will be equal to tan inverse of infinity, and we know that tan inverse of infinity is equal to 90 degrees. So in that case, this angle will be 90 degrees. That is what we have discussed earlier. Now, let us try to use the same concept to find out the current and the voltage across this capacitance. Find voltage and IT, VT and IT in the circuit given over here. We use actually you are asked to find out not in the phasor form, but in the time domain form, because when it is given, when you are asked to find out this voltage and current in small letters, it means you have to find it out in the time domain. Let us convert first this circuit into the phasor domain. I haven't changed this to the phasor domain, so I'll do it in terms of equations. For the voltage source 10 cos of 4t, it is given that 10 cos of 4t. That means this will be omega. Omega will be equal to 4. So since there is no angle, no phase angle of this, that means Vs is equal to 10 at an angle of 0, because it is 10 cos of omega t plus phi. Since phi is not given, means phi is equal to 0. The impedance, the total impedance of the circuit will be the impedance of this plus impedance of this, because they are in series. So it will be Z is equal to 5 plus 1 divided by j omega c, 5 plus 1 divided by 4j into 0.1. It is 0.1 farad. So it comes out to be equal to 4j is 0.4 inverse unit of 2.5, that is 5 minus 2.5 ohms. This is the total impedance that will be actually seen by the source. So the current will be Vs by Z. Vs is equal to 10 angle 0, that we have calculated over here. Z is equal to 5 minus j 25. We can calculate its magnitude as well. Actually, this is the rationalization of this. 5 plus j 25 divided by 5 plus j 25, it comes out 5 square plus 2.5 square. So after doing the all manipulation, this comes out to be 1.6 plus j 0.8, which is in the polar form 1.789 at an angle of 26.57 degrees. So the capacitor voltage, this is in the phasor form. We haven't converted into the time domain form. It will be simple. In time domain it will be 1.789 cos of 4t plus 26.57. So the voltage across the capacitor will be current that is flowing through the capacitor, that will be same current multiplied by ZC, whatever be it is impedance. So that I divided by j omega c, I is this value, j omega c is this, j omega c. So it comes out to be equal to 4.47 at an angle of minus 63.42 volts. So in time domain, that I have told you, it will be 1.789 cos of 40 plus 26.57, and this voltage will be 40 minus 63.2. You can see that here, that IT and VT, IT leads to VT by 90 degree. This IT leads to this voltage, because this is the same current that flows through this voltage. It leads to this voltage by 90 degree. That is depicted from here. The voltage difference from this to this, so the phase difference from this to this is 90 degrees. Now if somebody tells you what is the phase difference between this voltage and this voltage, it will not be 90 degree. It will not be 90 degree. It will be this much. So impedance combination, I will not go into the derivation. I can directly say that Z equivalent in case of series combination, it will be equal to the summation of the impedances Z1 plus Z2 plus if we have Zn, that is impedance placed in series, n impedances, so the total impedance will be the sum of impedances. So in case of parallel, so 1 by Z equivalent will be equal to 1 by Z1 plus 1 by Z2 plus dash 1 by Z1. So, or in case of admittances, the parallel combination will be the summation of the admittances. So if we have two admittances, two impedances which are connected in parallel, in that case, the total impedance will be equal to Z1 plus Z1 into Z1 divided by Z1 plus Z2. So using this impedance in series and parallel and other uh, concept that we just have discussed, let us try to determine the V naught, that's voltage across inductor across this, by using the phasor form. So converting in the phasor form, you can see 10 millifarad capacitor. I have to multiply it by 4 to get the omega C, and I have to multiply, sorry, I have to, yes, get the omega C, and inverse will be the reactance of this. So when we multiply omega over here, it will be 4 into 5, that is 20. It will be the impedance of the inductor. So I have converted it into this. You can see it over here. It is given Vs is equal to 20 cos of 4t minus 15. That is 20 cos of 4t minus 15. So that is this. So in phasor form, it is Vs 20 at an angle of minus 15. Here omega is equal to 4. So for 10 millifarad capacitance, its impedance will be equal to 1 divided by j omega c. So 4, that is omega c is equal to 10 millifarad. It comes out to be minus G25 ohms. So for 5 Henry inductance, it comes out to be G20 ohms. 5 into 4 is 20. So when it is in the phasor form or frequency domain, so it is now easy to calculate. Let us know Z1 is the impedance of 60 ohm resistor, that is this, and Z2 is the impedance of the parallel combination of 10 millifarad and 10 millifarad capacitance and 5 Henry inductor, that is this. So parallel combination will be Z1 into Z2 divided by Z1 plus Z2, that is this. Parallel combination means minus G25, this is capacitance, in parallel, this means parallel combination of G20, that is inductor. It will be equal to Z1 minus G25 into G20 minus G25 plus G20. It comes out to be G100. So Z2 will be this. So by voltage division principle, we have already discussed what is the voltage division principle. The voltage at this combination will be equal to this combination, that is Z2 divided by Z1 plus Z2 into this voltage. So that is what I have done. Z2 divided by Z1 plus Z2 into Vs. Z2 is J100 divided by 60 plus J100 into 20 at an angle of 15, that is the source voltage. So it comes out to be equal to this, that is 100 divided by J100 divided by 60 plus J100. When you solve it, it comes out to be this, and finally V naught will be equal to 17.15 at an angle of 15.96 volt. So converting to the time domain, it comes out to be 17.15 cos of 40 plus 15.96 volts. So please try to do these numerical at your home so that you may get some sort of understanding of the concept that we have just discussed. Okay, thank you. I will stop over here.